Laplace transform. C1, basic properties of Laplace transform. Here you can see transform. Yeah. This word gives us a new problem-solving approach. This is a, good problem-solving approach. Transform. Yeah. So before you solve the problem, so here, let me give you the background of this problem-solving approach. Very powerful problem-solving approach. All right, so our current problem-solving approach, straightforward. So we apply different techniques directly on the given question. Now this new approach, indirect, not direct. Okay. So before we solve it, we apply certain transform. Okay. Then change the domain of the question. The question, so there is some domain of the question, right? Yeah. So your environment, your working environment, we treat as the domain of apply certain transform. We change the domain to a different environment. Okay? Different environment, right? All right. Then, in different environment, then we have different tools. We have different tools. So with different tools, we solve that problem. Then we change it back to the original. Okay? We apply the inverse transform. Yeah? Because every transform, you should have an inverse transform to get back. Okay? Two-way transformations. Yeah? So we change the domain. Okay? From one specific domain to another specific domain, and do some work there. After we get a solution, we do inverse transform, get back to our original. So this approach, very powerful. This topic for any engineering student. All right. Another thing, before we start this, I want to give you another good example. Good example for engineering students. Another important type of applications, signal processing. You know that? Image processing, signal processing, video. Yeah. So the signal processing in general. In signal processing, this approach is used quite common. Yeah. What's that? Change the domain. Yeah. Because when you have digital signals, what's the domain you are working? Yeah. Digital signals. Okay. Yeah. Yeah. Spatial domain. Yeah. So we call time domain, right? Time. Yeah. So at different time, your signal changes as a function. So one is the time domain, but for image, spatial domain, right? X coordinate, Y coordinate, that's the spatial domain. Okay? Time domain, spatial domain. Then you apply Fourier transform. You change it to a different domain. After you apply Fourier transform on your signal, you change it to frequency domain. So it's not time domain, spatial domain. It becomes frequency domain. What do you have? All frequency, different frequencies. Okay? Yeah? So sine curve, cosine curve, the number of cycles per second, right? The frequencies. You will process your signals in the frequency domain. Yeah. So then you can do denoising, compression, a lot of applications, okay, in frequency domain. After you finish processing, then you do inverse transform back to the original domain, time or spatial domain. So for processing, people use this way all the time. Yeah. Yeah. So this approach, very important. Yeah. So today, let's look at the Laplace transform. Yeah. Basic properties. All right. Why we need Laplace transform? Yeah. All right. The key motivation, we will see the definition soon. Yeah. So just in the next slide, we will see the definition soon. The key motivation for learning about Laplace transform is the process of solving the ODE is simplified to algebraic problem. Yeah, this is the main reason we use that. Yeah. Because before you apply a Laplace transform, you solve ODE directly. Okay? Yeah. So we learn all those techniques. Yeah. Now, Laplace transform convert ODE problem to algebraic equation problem. Just algebraic problem. That means you do not need to solve ODE. You just solve an algebraic equation. Yeah. So most of you feel solving algebraic equations usually simpler than solving ODEs, right? Yeah, differential equations. Yeah. So you just use our basic algebraic scales. We solve algebraic equations. Then, after we get solution, we do the inverse Laplace transform back to the original domain. So we get original solution. That idea. Okay? Yeah. So very interesting. Yeah. The diagram like this. Later we will see example when we solve IVP problem, initial value problem. Okay? So we do not solve directly from ODE point of view. We do conversion. We apply Laplace transform, so we get an algebraic problem. So we get some algebraic equation after Laplace transform. Yeah. So, very smart, brilliant idea. Yeah. All right. Then, because now we are in a different field, different domain, different, environment. Yeah. Solving the problem by algebra, solving equation by algebra. Yeah. Okay. Yeah. So we get an algebraic function as the solution. Yeah, we have an algebraic function. Yeah. Then, in order to get the original ODE solution, we inverse Laplace transform back to the original environment. So we get a solution. Yeah. Yeah. So after you see it, the whole, just see some examples. So you will know how powerful is this method. Yeah. All right. This type of mathematics converts problem of calculus. Yeah. Because before the conversion, you have a lot of derivatives, second derivatives, higher order derivatives. Yeah. Those, calculus related content. So you convert problem of calculus to algebraic problem. Yeah. Algebraic, addition, multiplication, division, sine, cosine, no derivative anymore. Okay? You won't see any derivative. Yeah. Yeah. So it is no operational calculus. Yeah. Yeah. So think about how can that possible, right? Yeah. So after you see it, you will appreciate this idea. Yeah. All right. So here, right. Two advantages, main advantages of this method. Yeah. Two. Okay. First, problems are solved more directly. Yeah. So more directly. Yeah. Yeah. Here, yeah. At the beginning, I said indirectly. Yeah. Yeah. But here, more directly. There is some specific meaning here, yeah, because when we look at from different view, it's more directed. Initial problems are solved without first determining a general solution. In that sense, more directly. Our ODE, we need to find a general solution first. Then we, plug in initial conditions. To two steps. Yeah, two steps. This one we mixed initial condition. When we apply Laplace transform, we need to use the initial conditions. So when we find algebraic solution, the initial condition is already inside our algebraic equation. Yeah. So we just find the final solution directly. Yeah. So that's the meaning of directly. Okay? Just one step, we get a final solution. Yeah. That's the meaning. Yeah. So here, directly, indirectly, the meaning is different. Yeah. The meaning is different in that sense, directly, indirect. Yeah. Non-homogeneous ODEs are solved first solving the corresponding homogeneous value. Yeah, yeah. So here you can see the typical two-step approach now become one-step approach. Yeah. 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 So that's the first benefit. Second, the method is particularly powerful for problems with inputs that have discontinuities. Yeah. We haven't had many problems with discontinuities. Yeah. But I remember I gave you one application problem, the gun problem. But that's not discontinuity. That's the piecewise function, right? That gun problem, gun barrel problem, that one, remember? There is no discontinuity, but it's a piecewise function. The force, the gunpowder, the force is a piecewise continuous function. But here, we can handle discontinuities. Yeah? The function, not continuous, discontinuous. Okay? Yeah. So there is a jump. At several places, there are a few jumps. Yeah. But this method can still handle those situations well. Yeah. Yeah. So we will see that. Yeah. Yeah. Heaviside function, that's the step function. You change very sharp. So it's step function. Heaviside, step function. Okay? Yeah. All right. Dirac's delta function. Yeah. So that's another very special. Yeah. So Dirac delta function. Yeah. So we will understand that this is a very special function. Yeah. Dirac delta. Yeah. So the function value is hard to define. We can only define the function by its integral. Its integral can be defined, but the function, it's hard to define the function explicitly. Yeah. Define the function. Okay? It's hard to define Dirac function directly. So you can see the behavior could be very bad. Yeah. But this method can still handle the functions with very bad behavior as well. Yeah. All right. So yeah. So that's some nice properties. Yeah. Definition of Laplace transform. Now we need to start doing calculation. What's the definition of Laplace transform? This integral formula. Yeah, look at that. Yeah. Given function little f, that's the given function. Okay? Given function. Yeah. Later we will describe the condition for this given function, little f. Yeah. So now just you can assume some function that is good enough. Yeah, it's good enough. Yeah, later we will define what do you mean good enough. What's the meaning of good enough? Yeah. All right. Then you apply Laplace transform, change to, it's like a different domain. Okay? Yeah, different domain. Capital F of S, that's the transformation output function. Capital F of S. The variable will also change. Okay? The variable will also change. Yeah, we use S variable. Yeah. T variable. So in the original domain, we use T variable. In a new domain, we use S variable. Okay? Yeah. The function related little s and a capital little f and a capital F. Yeah, related. just you take this integral, okay? Yeah. The integral from 0 to infinity, and you multiply a special function, e to the negative s times t. That special function. That special function, when you multiply that, yeah, so you get a new function with good properties. Yeah. Okay? All right. So we will study all the properties, all the basic properties of Laplace transform. Yeah. Yeah. All right. Kernel concept. Yeah, here. When you multiply the special function, yeah, there is a math concept called a kernel. Yeah, it's a kernel function. Yeah. So mathematicians, they use this notation, k of two variables. It's a two variable function, st, yeah, the kernel function. Kernel function for this operator, yeah, here we call it operator. Okay? The transform, sometimes people also call it operator. In order to define an operator, what's the operator? You apply an operator on a function, you get another function. Yeah. Here, this situation. Yeah. Just a different view. Yeah. Different way we describe the situation. Yeah. All right. So here, this operator, we use this specific kernel function. Yeah. Here, just terminology. Yeah. You do not have to use these terminology. Okay. Yeah. Even you do not know these terms, you can do Laplace transform. Yeah. All right. Yeah. So here, this operator is defined with the kernel in this way. Yeah. Yeah. Here, this is just a, typically mathematicians, they like to use this abstract way to study operators. Okay. For us, it's not important. Okay. If we call it the kernel or not, it's not important for us. Yeah. For us, important thing is we know how to apply Laplace transform on a given function. That's important. Yeah. All right. Then inverse Laplace transform. So this time, after we find a solution, algebraic equation, we find a solution, we need to go back to the original domain. Yeah. We get a solution for the original ODE, so we need to apply inverse Laplace transform. Yeah. Yeah, but here, one thing. So here, the inverse Laplace transform. So here you can see there is no specific formula defined for the inverse transform. Yeah. So the inverse is after we have Laplace transform, there we just go the opposite direction because this capital F corresponds to that little f. Now you just imagine when we apply an inverse Laplace transform, we get that little f. Yeah. Here, the definition of this inverse not explicit. You cannot. What's the formula for that inverse Laplace transform? We cannot see it. Here we just based on the result. Yeah. The reason we can say this because we have that before. We have the Laplace transform before. We just go backward. So we have the inverse Laplace transform. Here the situation is like that. Not like Fourier transform. Fourier transform, the inverse transform, we have specific formula. Okay? There is a Fourier transform, inverse formula. Yeah. But here, Laplace transform, we cannot write it explicitly because we don't know how to write it. The question is, we don't know how to write it. Okay? So we use this indirect way. This is the indirect way because we know the result. So we know we can go backward like that. Yeah. Yeah. Later, yeah, you may ask question, if we do not have the definition of inverse, how do we do the calculation? Yeah. So we have we have big table, okay? Table, Laplace transform table from left to right. When we do inverse transform, we just go backward, okay? We look up our table, left column, right column, yeah. Left column function, after you apply Laplace transform, you get right column function. To do inverse, we look at the right column first. When we apply Laplace inverse transform on the right column, we get a left column function. Yeah, we just look up in the table. Yeah. All right. Yeah. So here the definition is not obvious. Yeah. Not explicit. Yeah. Hidden. Yeah. Definition is hidden. Yeah. All right. Yeah. But this property. Okay. So Laplace transform inverse, you get to the original. Okay. Get the original. Then inverse. Capital F, then Laplace, yeah, same function. Yeah. So all inverse operations should have the same property. Yeah. So you can go two directions. Yeah. So switch, two different domains. Yeah. Yeah. All right. Then linearity, the property. Yeah. Linearity. This simple property. Yeah. Because the definition of Laplace from integral, integration, integral. Integral, we know the integral operation has the linearity, right? Property. Derivative operation has the linearity property, right? Integral operation also has the linearity property. Yeah. So the Laplace transform inherits the linearity property from the integral operation. Yeah. So it's very natural. Yeah. Yeah. So, and it's very useful because when we split a function into many terms, yeah, the combination of multiple terms, we can always apply the linearity property to calculate Laplace transform of individual terms, like this. Yeah. 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 And each one, Laplace transform of each basic function, so we calculate a table. So we put there, okay, table. Yeah. So we can look up the table. Yeah. Yeah. All right. Laplace transform of simple functions. Yeah. Here, let me show you Laplace transform of several simple functions. Yeah. So later we put them in the table. So we just look up the table, yeah, when we do the calculations. Yeah. All right, the first one, let's calculate Laplace transform of 1, constant 1. Yeah. So by the definition, yeah, here, I put the Laplace transform definition there. So we take that integral here. Yeah. So it's easy, yeah, so you treat S as constant. You treat S as constant. So you do integration by parts. Integration by parts, the infinity. So here, because after we get this expression, we need to evaluate the expression at these two limits. Okay? Upper limit infinity, lower limit 0. Yeah. To make it converge, right? The upper limit at infinity, to make the function converge, S must be positive. Negative S. If S is a negative number, then it won't converge, right? Yeah. If S is a negative number, negative is a positive. Positive times infinity, it's infinity. It is infinity. So we don't want to have the value infinity here. Yeah. So for that reason, we require S must be strictly positive number. Then the value can be evaluated. The limit exists. Yeah. All right, so that's the first one. Second one, calculate the Laplace transform e to the a t. Yeah, a constant, t variable. Yeah. Yeah. So this one, we apply the formula. Yeah. So here the same structure, same base, e base function. Yeah. So there we combine the exponent part. So here in the parenthesis, s minus a, so this number has the same role of the S1. Yeah. Same position, yeah. Same situation. Yeah. So the result, 1 over S minus A, but remember the range of S, it should be S greater than A. Otherwise, it is not defined. The value is not defined. That's the only thing you need to be aware of in calculation. Yeah. All right. Yeah. The basic requirements here. Yeah. Number 3, Laplace transform of hyperbolic, right? Yeah. Cosine hyperbolic. Yeah. 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 By the linearity property, because 1/2 e, yeah, sum of these two terms, we split. Yeah. And each one we can use this formula. Yeah. All right. So then we simplify it, we get this expression. Okay? Yeah. Yeah. Hyperbolic cosine function. All right. Another hyperbolic function, similar. Just to change plus sign to minus sign. Okay, yeah. So then we get that expression. Yeah. All right. Number 5, cosine omega t. Yeah. This time, cosine. Okay. Cosine. This one a little harder than others. Yeah, because the cosine structure different from e. For the previous examples, typically e-based functions. But here we change to cosine function. Yeah, so here we use the notation LC to represent this Laplace transform. Yeah. Then we also consider the sine LS because we want to calculate them together. Yeah. Yeah, because we can derive recurrence relation between these two functions. Yeah. So we consider them together. So the first one, when you take integration by parts, so you just do carefully integration by parts. Yeah, from the definition, you will get expression with LS. Yeah. LC, you need to use LS value to represent. Yeah. Similarly, when you calculate LS, you need a LC expression to represent it. So you get a linear system, right? Simple linear system. Yeah. So you need to solve both equations as a linear system to find solutions. Yeah. LC, LS, yeah, expressions. Yeah. All right. Yeah. So the last one, calculate this one. Yeah. Yeah. Power function t to the n plus 1 here. And why n plus 1 for convenience? Yeah. You will see. Yeah. If you use this plus 1, then the derived formula more convenient. Yeah. Plus 1. Okay. Yeah. All right. So here. Yeah. Here. Integration by part. Yeah. So here. Yeah, because we do integration by part. Yeah, because I need more space, so I do integration by parts here. Yeah. All right. So then, because this term is gone. Yeah, we have second part. Yeah. Then, so here. So the first term is gone. Okay. Yeah. So after integration by parts, this term is gone. Oh, sorry. Yeah. Gone. Okay? All right. So we just have m plus 1 over s. M plus 1 over s. Then, recursion, Laplace transform, this time on the function with t to the n. T to the n. Yeah. So here you have this relation. Okay? Yeah. Relation. But you can do this iteration again and again, and at the end, you get this expression, n plus 1 factorial over s to the n plus 2. Yeah. Okay, yeah, so that's these 7 basic functions, Laplace transforms. Yeah. Here you can see the computation is not too complicated. Yeah. Yeah. So we can handle. Yeah. So if you compare this kind of computation with our previous topic, power series, yeah, I feel the power series computation more complicated, right? Yeah, we do summation, you need to do much more work. Yeah. Yeah. Here, relatively less work than that power series based solutions. Yeah. Yeah. Now, power series, that topic, I haven't finished. I have part of it. Yeah. Yeah, but this topic is more important. So let me do this topic first. After I finish this topic, so then I just use probably another half class, not a full class. Half class, I try to close that topic, a power series topic. Yeah. When I assign you exercise questions, just straightforward power series solution. You expand, you do calculation, you write a solution. Yeah. So I will not ask you to prove any properties. Just solve ODE. Relatively simple. Yeah, not too hard. Yeah. Yeah. Just let you get an idea. Yeah. So there is another method you can use. Yeah. All right. This is the table. Okay. Yeah. Here. Yeah. We have our first table for basic transform. Yeah. Yeah. In our textbook, we have one section. Later, we have a larger table. Yeah. So, yeah, one section, longer table. Yeah. So this first is shorter. Yeah, shorter table. So when we do calculation, we need to look at the basic formulas. Yeah. Just like when we do integrals, many times we need to look up in some tables. Yeah. Yeah. For integrals. Yeah. All right. Laplace transform of gamma function. Yeah. There is a function, gamma function. Yeah. Gamma function, the definition of gamma function. This is the definition of gamma function. Yeah. Yeah. And in our previous topic, actually there is one topic we need to use gamma function. Yeah, but I skipped that. So this is the first time we see the gamma function definition. Nu plus 1. Yeah, the definition. Yeah, we use the define nu plus 1. Yeah. Because in the integral, we want the t exponent of t is nu. Yeah, nu. Yeah, so then nu plus 1. Okay, all right. Yeah, gamma function. Now, gamma function for some special problems very useful. Yeah. Yeah. All right. Then, when we apply integration by parts, we get recurrence relation equals nu times gamma of nu. Yeah. That's pretty good. Yeah. That's a nice simple recursion. Yeah. That's simple recursion, right? Quite simple. Yeah. But here, look at the range of nu, just greater than -1, and it's a real number. It's a real number. Usually not an integer. Not an integer, usually. It's a real number. Okay? Yeah. So we define this gamma function. Okay? All right. But if we look at the integer case, yeah, when nu equals integer, it's just a factorial. Yeah, because you do iterations here, recursion again and again, so you will get gamma of n plus 1, it's a n factorial. Yeah. So you can see this gamma function, you can treat it as a generalization of factorial. How about that? Yeah. Because the definition of factorial, you can only define factorial on positive, non-negative integers, right? Yeah. You can define 0. Yeah. You can define 0, 1, 2. Yeah. But you cannot define factorial for negative integers, right? Yeah. Do you know what's the 0 factorial? Any of you know that? 0 factorial? 1. You all know 1, right? Yeah. Good. Yeah. Very good. Not 0. Yeah. Don't say 0. It's 1. Yeah. All right. All right. Yeah. But the question is, when nu is non-integer, any real number, non-integer, then our gamma function we can define, if nu greater than -1, we can define this gamma function. So you treat it as an extension of factorial. Yeah. All right. Yeah. All right. So then, yeah. So that Laplace transform here. Yeah. But look at this time. We expect n to be integers, right? Yeah. Non-negative integers. Yeah. But can we consider the exponent here non-integer, real number? Yeah. Right. Yeah. 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 Actually, we can. Yeah. You know. So in our table, in our previous table, we have that. Yeah. Let me go back to the previous table. This table, look at t to the a. Yeah. A positive, non-integer. Yeah. We have that formula. Okay. Gamma of a plus 1 over a to the a plus 1. For non-integer, we have that formula. Yeah. Gamma function. Okay. Yeah. All right. So we will not do a calculation. Yeah. All right. Yeah. So here, let's move to another property called the first shifting theorem. Another property we can use when we do Laplace transform. Yeah. All right. So this shifting theorem, we replace s by s minus a. That's a shift. Okay. By a. Yeah. So f of s minus a equals that. Okay. Yeah. So then we split. Yeah. Laplace transform. We multiply original f function by this e to the at function, exponential at function. Yeah. So this property, yeah, this simple property, pretty simple, right? Yeah, pretty simple, straightforward property. Yeah. So that's our first shifting theorem. Yeah. Yeah. First shifting theorem. Yeah. So when you do Laplace transform, if you see an e term like that, multiply some function, then you can use this formula. Okay? The inverse, you can use that formula. Yeah. Yeah. So sometimes it's useful. So you can simplify. Sometimes when you apply this theorem, so you can simplify your calculation of Laplace transform, inverse transform. Yeah. Okay. All right. So then, yeah, I hope before we finish today, you see a few calculation examples. Yeah. Example. Now we see example. Yeah. Inverse Laplace transform. Yeah. So the first example, let's look at inverse. Yeah. All right. Yeah. The inverse. First, I want to. Yeah. So this one. Oh yeah. So this formula, the first shifting. Yeah, so this one show you the first shifting theorem. Okay, number 11, we just multiply that e function to cosine. So here you can see we just do a shift operation on the Laplace transform of that cosine. Yeah, so very convenient. Yeah. Yeah. So, all right. Yeah. Another for sine inversion. Multiply this e term, yeah, we do shift operation on s. Yeah. Yeah. Very easy. Yeah. All right. Now, example. Let us calculate Laplace. Yeah. So here, the question is this. Yeah, actually, we calculate inverse. So it is known that Laplace transform of f equals this fractional expression. Yeah. Yeah. All right. Yeah. Now we want to calculate original function f. That's the inverse Laplace transform. Okay. Find f function by taking inverse Laplace transform. Yeah. All right. So here, the first thing, you do not know the definition of inverse Laplace transform, right? Yeah, nobody knows that explicit definition of inverse. But we can decompose the fractional representation function inside the parentheses to some functions that can be represented by the right column functions. Then we apply the linearity property and put them together, reverse, we get f. That way. Okay? Yeah. So let's look at the details. Yeah. All right. First, we need to decompose. First, the denominator, s plus 1 squared plus s plus 1, look at that, little a. Okay? S plus 1 squared corresponds to that shift, little a. Okay? All right. Yeah. The numerator, we try to use the same shift number. Okay? Yeah. A. So here you know that a, little a, -1, right? Little a is -1. So by the linearity. So the first thing, by linearity, you take that 3 out, minus, the second, 140, you take 7 out, that's 20. You try to match the structure in one of the right column function, omega squared. You try to match that structure of some of the right column functions. Okay? Yeah. So here you target that function. Here you target this function. Okay. Yeah. All right. Then we can apply that first shifting theorem. A, So here, because we know a is -1. So that e to this, okay? Yeah. All right. Then omega is 20 here. Omega is 20. Yeah. So cosine omega t. Yeah. So that's the result of this inverse transform of the first part. Okay? Yeah. Not too bad. Yeah. Not too bad. The second one, apply that function. Yeah. Minus 7 e to the negative t, a negative t, then sine omega t. That's the result. Okay? That's the inverse of this Laplace transform. See? That's how you do the calculation. Yeah. Basically, you do decomposition. Okay? Yeah. Yeah. So you have the partial fraction background. Yeah. Similar to your partial fraction decomposition. Yeah. Yeah. Try to decompose in some standard structure. So here, our standard structure like that. Okay. Those things. Yeah. All right? Yeah. So, yeah. Yeah. So then, you can calculate in this way. Okay? All right. Yeah. So this is just introduction. Yeah. After the midterm. Yeah. After Thursday midterm. So next week, we continue. Next week, 2 classes, we hope we finish this topic. Yeah. All right. So then, after that, so you